Saxon's Calculus, Lesson 83, is about continuity of functions. So there is a series of important boxes in this lesson. The first two of them are on page 409. And the first one is maximum minimum value existence theorem. It says, if f is continuous on a closed interval, a to b, then that function has a maximum value, they're calling m, capital M, and a minimum value with a lowercase m, somewhere in that interval of a to b. And we kind of talked about that before in an earlier lesson. Second box, the intermediate value theorem. If the function is continuous on the closed interval of a to b, then n is a number between the max or the f max and the f min, then there is at least one number called c between the a and the b for which the function of plugging in the c gives you the n. Wordy, but if you think your way through that, it does make sense. Then on page 410, they remind you that both a left-hand limit and a right-hand limit must exist as x approaches c. The limits must be equal, and the value of the function at c, which is the same answer you get when you plug c into the function, must exist and must equal both the left-hand and the right-hand limits. And then their next box is the definition of continuity at a point. So a function f is continuous at a point c if f exists at c and the limit as it approaches c from infinity basically gives you the answer c. And then definition of open interval continuity. A function f is continuous on an open interval from a to b if it is continuous at every point on the interval. So if there's no gaps, it's continuous. Well, that was as we would expect. And then their last one is definition of closed interval continuity. So open interval was, it has to be continuous at every point. A function is continuous on a closed interval from a to b if it is continuous at every point between a and b, as it said before, and if the function is defined at both a and b with the limits that there's the limit as x approaches a from the positive is the answer you get when you plug in a, and then the limit as x approaches b from the negatives is the same answer you get when you plug in b. And those may be easier to actually see and evaluate what they're actually saying if you read them yourself a couple of times and maybe work through a quick graph or picture of some sort may help you. Now, example 1 says, given that f is defined on an interval of 1 to 3, if f equals 1 gives 1, and f equals 3 gives 7, does a number c exist? And then it's listing between 1 and 3. So is c greater than or equal to 1, less than or equal to 3? So is c falling in between those? I did say or equal, yes. Such that f of c is 3. Okay, so if I'm picturing between 1 and 3, I've got some sort of graph happening. 1 gave me a 1, 3 gave me a 7, so way up high. So it's obviously either a straight line or curving or doing something in here. Will it guarantee that some spot gives me an answer of 3? Well, instinctively I want to say yes, but what happens if there's a hole in my graph there? Then no. So the answer is not necessarily. It's likely, but it's not necessarily. Example 2. Suppose f is a function that is continuous on a closed interval of -1 to 3, Which of the following could be the graph of f? Debating whether I need to actually graph these. Maybe I can just talk us through it. So from -1 to 3, all of my graphs show -1 to 3. They all show that. So none of them are thrown out for that reason. Then it is, okay, I was rereading the instructions. It is continuous, so there can be no gaps. All right, C has a jumped gap, so it's thrown out. Oh, it was continuous. That's the other reason why it's not. Okay, so A, B, and D are all continuous. However, A and B have open circles at the end. So they are thrown out. The only graph I can keep is D. Yeah, I can't do it. All right, example 3. Let f be a piecewise function defined as the absolute value of x plus 3 when x is less than 1, and ax squared plus bx when x is greater than or equal to 1. And technically that was f of x equals that piecewise function. Find the values for a and b so that f will be continuous. Well, from -infinity to infinity, that pretty much means everywhere. All right, they suggested starting with a rough sketch thereof. Okay, so between less than 1, not equal to 1, so I couldn't plug in 1. Well, I can, but it would be an open circle. That would be at 4. Okay, then 0 would be at 3, -1 would, that goes back to 1, that goes back to 4. Okay, so it's whatever it's doing here, it's the start of a V, but this is an open circle because I couldn't have it at 1. Then here, what's happening at 1? Well, it's a parabola of some sort because it's x squared and a bx, and that's only from 1 and above. So wherever this would start, and it could be above it or below it, I don't really know, it's going to have a colored in dot and then a part of the parabola. It might be the vertex point, it might not, it don't really know. Okay, so there's the rough sketch that they talked about. Now, find the values for A and B. So it's going to be continuous if this dot actually fits here. So what made this one work would have, at 1, would have been 1 plus 3 is 4. So if this is equaling 4, then it's continuous because this dot would actually be falling in the hole, as I said. So I don't think I can come up with specific numbers because there would be a series of them. Anything that would make this equal to 4. So if A and B has a sum that is 4, it is then continuous. Oops. So I guess that would be the simplest way to write that answer. Definitely out of space. Example 4 says, let f be a piecewise function defined as follows. So f of x equals, and I'm going to pause while I write this one out. All right, so on this one, rather than doing a sketched out graph, and this is supposed to be a fraction, x squared minus c squared over x minus c. I just derailed when I was writing it, and so that looks really terrible. But that is the fraction when x is not c. And that's a good thing, because if I use c, then that would give me a 0 in the denominator and I would have a huge problem. So they're saying, as long as I don't use c in this equation, what kind of a picture would I be getting? Well, something squared minus constant squared. I might actually, picture that as factored out x plus c, x minus c, and so then the x minus c is canceled. So would I have any reason for this to not to have a gap or a problem? Nope. And then for plugging in c itself, because again, I couldn't use c, so I potentially have a gap, but it says if I plug in 2c there, do I have a problem where it does not fit into what this was doing? And no, I would be okay with plugging it in only at c, so therefore it is continuous no matter which number I'm choosing, so from negative infinity to infinity.